Good morning, good afternoon, good evening, from whichever part of the world you are in. Today we have with us Daniel. He's Strategic Innovation Manager at Nuclear Restoration Services. He is one of the founders of the ITS Special Interest Group on Geological Disposal Facilities, an initiative grown from his role as a technical expert supporting the International Atomic Energy Agency work on transitioning to underground activities for GDF delivery. Daniel is a UK government official and a chartered engineer. With the Institution of Civil Engineers, he has a background in underground engineering and major program delivery. Formerly the tunneling and underground space expert on the UK's GDF program, he is currently head of strategic innovation focused on nuclear decommissioning of the UK government within the Nuclear Decommissioning Authority Group. Daniel is also co-chair of the UK Government Infrastructure Industry Innovation Partnership I3P, and is the chair of International Affairs on the BTS committee. We welcome you, Daniel, on our TAIym webinar platform. Over to you.
Thanks very much. Well, I'm going to share my screen with you, and you let me know when you can see that.
Yes.
Okay, and it is in presentation mode now, yeah?
Yeah, it's in presentation mode.
Perfect, absolutely perfect. So look, again, good evening, good morning, good afternoon, wherever you are. I'm sat here in Vienna at the International Atomic Energy Agency this week. So it's really fortuitous that we're going to be talking about geological disposal. I've just spent the whole week talking about it here at the UN headquarters in Austria. So first off, thank you so much for inviting me to speak today about geological disposal for radioactive waste. It's genuinely exciting to be here and share with you what I've learned over the years in what is quite a fascinating field. So those of you who haven't met me yet, you heard in the introduction, I'm Daniel Garbutt. And I'll try and keep this sort of a little bit organized because, to be honest with you, I'm involved in quite a few different areas. So I'll start with my main role. I work for the UK government in nuclear decommissioning, so as head of strategic innovation within the NDA group. And before moving into innovation, I was the tunneling and underground space expert for our national radioactive waste disposal program, which is actually how I became obviously so involved with geological disposal. And on the tunneling side, I represent the UK as our member nation representative to the ITA, and I also co-chair the BTS ITA sort of International Affairs Committee, which keeps me connected to what's happening in tunneling globally. I also co-chair something called I3P, which is the Infrastructure Industry Innovation Partnership, bit of a tongue twister. But in simple terms, that's where we sort of bring government and private companies together to drive innovation across UK infrastructure. So breaking down those traditional barriers and finding better ways of working. And internationally, I've been working with the International Atomic Energy Agency as a technical expert. So this has been incredibly rewarding. I'm a contributing author on a publication coming out soon, which focuses on managing that crucial transition to actually building geological disposal facilities underground. And I'm also a contributing author on another publication, which is what I've been working on this week, that's about research and development programs to support geological disposal. And as you've just heard in the introduction, I recently co-founded a new special interest group within the ITA specifically for geological disposal facilities. And I'm pleased to announce that Professor Arnold Dix agreed to chair this group, and together we both sit on the steering board, which is focused on growing our collaborative partnership with the International Atomic Energy Agency and the global waste management programs for nuclear waste disposal. And what we're doing is it's quite unique. We're bringing together the tunneling world and the nuclear agencies and waste management organizations globally to support the transition from scientific underpinning to engineering delivery. So today I'm going to take you through what GDFs are, what the science behind them is, and what different approaches are going to being undertaken to GDFs, and what can we do or you do as the underground engineering community to support this really important global mission, I guess. So now you know who I am. Let me ask you something, and I don't expect an immediate answer, obviously. Rhetorical question, but do you know what geological disposal facilities are? We call them GDS for short, but I suspect most of you won't be familiar with them. And there's a good reason for that. They don't fully exist yet. So what is a GDF then? I think we can see on the slide here, you'll probably paint 1,000 words, but they are mostly exactly what the name suggests. They're deep underground facilities for disposal of nuclear waste, but they're specifically for higher activity nuclear waste. And I'll come to talk about that a bit later on. But to be clear, there are some disposal facilities already operating around the world, but these handle low level or intermediate waste, and they're typically not that deep underground. Even those are pretty rare globally as well. So when it comes to the really radioactive waste, so that's the high levels. That's what we call, when we talk about levels, we talk about the level of radioactivity associated. So that high level stuff. There's currently no operating disposal facility anywhere in the world. So these facilities will be seriously deep. We're talking up to 1,000 meters below ground. So you can see on the picture, but so you don't necessarily need to bring it to your mind's eye, but you've got a network of vaults and tunnels where waste containers will be stored safely for millennia. And that's the timescale that we're dealing with here. It's a significant timescale. But here's the reality of the fact: every nuclear nation will eventually need a GDF to dispose of its higher activity waste. And this covers quite a range of sources, such as experimental reactor waste, spent fuel, and waste from defense programs, etc. Some countries might also use the same facility for intermediate level waste, which may include radioactive materials from industry, reactor decommissioning, medical treatments, research facilities, and so on. And just to be clear, however, this isn't just an idea. This is a highly studied, highly scientifically underpinned approach that the nuclear nations have been collaborating on for many decades. And many nations have long-running experimental programs within underground research facilities that are supporting their advancement towards implementation of final disposal. And we'll come back to that topic a little bit later on. So how does the concept of geological disposal actually work? Well, at its core, the GDF concept works on a simple principle: isolation and containment. We're removing the hazard from any potential receptor by putting barriers between them and placing them at such a depth that they are isolated from any of those receptors. Now, I don't want to turn this into a sort of nuclear physics lecture, and I'll assume you're all well-read engineers with a basic grasp of quantum physics, but let me outline just sort of quickly what it is we're dealing with. Radioactivity is a naturally occurring phenomena. Most elements are unstable, so they have excess energy in their nucleus, and over time that energy gets released, either as either spontaneously or when impacted by something else. And this causes the element to decay until it reaches a stable point where it can no longer change. Now, this decay can happen very quickly, or it can take an incredibly long time. And we measure this using something called, or we term it as a half-life. A short half-life means fast decay, and a long half-life means slow decay. And the key thing is this decay process can essentially, well, it does damage living cells, electronics, and so on, which is why shielding and safety protocols are absolutely essential. And that, simply put, is the purpose of a GDF, to shield the waste safely from living things until decay no longer occurs. But because of the variable half-lives of our waste inventory, and every country will have a different makeup depending on what type of nuclear activities they have. We're talking about hundreds of thousands of years, and in some cases, even up to 1 million years plus. The radioactivity levels also influence how deep we need to build these facilities. So, how do we achieve this isolation? We use two types of barrier systems that work together. The engineered barrier systems, the EBS, and the natural barrier systems, the NBS. And each barrier must be capable of stopping or slowing down any of the radionuclides on their journey to a potential receptor. But crucially, they also need to work together as a single integrated system. And that system is the GDF itself. So let me break down the engineered barrier system first. We start with a nuclear waste package that goes into a special disposal container or canister, depending on what the national definition of that is in your nation. And these are specifically designed for long-term durability and corrosion resistance. In some countries like Sweden, they use copper canisters as part of what they call their KBS 3V disposal approach, which means it's disposed of vertically. And we'll touch a little bit on that later. And these containers, they're then placed into disposal vaults or boreholes within mined or excavated underground systems and backfilled with inert material like bentonite. Once the vault is full, it's then what we call termed plugged and sealed. So the engineered barrier system includes the waste container, the backfill material, and to some extent the tunnel lining itself, as well as the plug and the seal. The natural barrier system is the geological setting where we are going to be disposing of the waste. So everything matters here. The depth, the natural ambient temperature, the hydrochemical and geochemical makeup of the rock, how it transmits heat, the hydrology and the mechanical properties. All these factors work to arrest or slow down any potential radionuclides that might escape from the engineered barrier system. And here's the clever bit. If a radionuclide does escape into the natural barrier, the pathway back to any receptor should be so long that by the time it could possibly reach what we would call the biosphere, it will have decayed to a harmless background radiation level. So it is no longer going to cause any of those issues like damaging the cells or causing any problems with man-made systems, etc., etc. So how did we get here? How did we work out this was the right approach? Well, as underground engineers, you'll all be used to working to deliver a function within a program, a tunnel for a road, rail, wastewater, power, whatever it might be. You design and construct the tunnel to carry people to work, to bring power to and water to homes. The tunnel itself is never the objective. It's simply a means to achieve the outcome of the program needs. And it's no different for radioactive waste disposal. But in the case of a GDF, and this is quite an important for you all to sort of take away from today, is that it's about delivering science. And that's the asset that you're focused on delivering with a geological disposal facility, science itself. And because of this, the execution of these programs will be quite different from delivering the other types of underground assets you're familiar with. And we'll explore that a bit later. As I realize there's lots of exploring later on, but you'll come to piece the story together as we move through. But for now, I just want to highlight something crucial, that there are decades of scientific underpinning and experimentation behind the GDF concept. For those of you who aren't familiar with it, the International Atomic Energy Agency is a UN body that's responsible for overseeing, guiding, and supporting nuclear applications for peaceful purposes. Their motto is Atoms for Peace. This comes from a very famous Eisenhower speech in the 1950s when the IAEA was established. But they're not the only international body with an interest in this field. The OECD, for instance, has its Nuclear Energy Agency, which promotes similar objectives and provides another forum for collaboration. But today I'm just going to focus on the IAEA's mechanisms, since this is where I am today. This is and it's the forum that I am most familiar with. So I'm going to focus on their mechanisms for collaboration in building the case for GDFs. And then we'll look at how the ITA is supporting this work. So the IAEA has something called the URF network, and that's the Underground Research Facility Network. And here's how it came about. As the various nations have been developing their scientific cases for GDFs, they've naturally needed to carry out experiments in analogous underground settings to verify their initial hypotheses and validate their theories. So this network has been running for decades now, I think good few decades. And it reaches across the entire IAEA membership. So essentially every nation that needs to dispose of nuclear waste. So what the URF network does is that it provides its members with a platform to assess and share best practices or good practices. I think best practices is frowned on as a word these days. Good practices in developing, evaluating, and implementing geological disposal solutions. We're talking about intermediate level waste, high level waste, and spent nuclear fuel. So the emphasis is really on understanding how these underground research facilities can support successful disposal program development and implementation. So think of it as a giant community of practice and learning for geological disposal. And it's where members can assess and share what works, what doesn't, and crucially, how to use underground research facilities to support actual implementation of geological disposal and the development of the safety case and safety assessment process. And the network is open to organizations with specific responsibilities for establishing, developing, and providing the scientific basis for or even implementing deep geological disposal projects. So through this network, along with various other multilateral and bilateral relationships between member states programs, this is where the science has progressed and validated to support the concept of geological disposal. And this is how the global nuclear nations have come to agree that this is the best way forward. So just going to give you a little bit more information about what an underground research facility is. So as I mentioned briefly earlier, it's often analogous to the conditions that you'd find at a potential geological disposal facility. And some facilities have been in operation since the mid-1950s, and many are extensions of existing mines or tunnel systems, but others have been purpose-built. And they can be built in similar geology at similar depths, either close to a possible disposal site or somewhere completely different, as long as the conditions match what you find at the host site. And Sweden provides quite a good example for this. Their URF at Esper Laboratoriet near Oskarshamn, which is south of Stockholm, is actually a few hundred kilometers away from the actual GDF site, which is near Forsmark, which is north of Stockholm in Östhammar. So why the distance there? Well, the geological conditions at depth are fairly consistent across the Fennoscandian Shield, so they don't need to be right next door. Other countries have taken a different approach, though. France's URF at Beur and China's at Beishan are much closer to the potential final disposal sites. And we tend to think of these as sort of area specific URFs. So think of a URF as a giant science experiment. Its entire purpose is to support the development of what we call a safety case. And I mentioned that word before, and that's used for safe disposal. And there's a slide on that later where I'll give you more detail, but essentially the safety case is the fundamental process and document that demonstrates the GDF will meet its objectives. Within these facilities, researchers conduct all sorts of experiments. They test waste and placement technologies, they study how to backfill and how the backfill and the buffer materials behave. They model long-term disposal behaviors, all of it empirical, hands-on work. And this gives the GDF scientific community the certainty and the validity they need for their disposal canister designs, handling procedures, long-term durability predictions, and so on. So these facilities have also been crucial for understanding ground behavior in the specific types of geology targeted for disposal faults, disposal areas. And this is absolutely critical. You need to understand, you need this understanding to underpin your safety case, to gain regulatory and governmental approval, and ultimately to get your license to construct and then begin disposal operations. So URFs, they typically come after many years of initial research and development. They're not meant, they can be done in the generic phase at the very beginning, and they are part of that growing research and development phase for underpinning the need for a GDF and the safety of a GDF. And what goes alongside these URFs is a very extensive geological screening and cataloging process as well. They're not cheap. And they represent a massive commitment by a member state or a nation with a program. But here's the interesting aspect. Not every nation that needs a GDF will build its own URF. And there are two nations that stand out in this regard, Canada and the United Kingdom. Now, Canada did previously have an underground rock laboratory, but with their modern program, they don't have a URF, and the United Kingdom is also not focused on having a URF. Instead of building these URFs, they've chosen to carry out extensive geological investigations to narrow down possible sites and develop their safety cases progressively as they go underground. And they're also collaborating with nations that do have URFs. So conducting relevant experiments that support their own safety case development. The national regulations allow for this approach. But that flexibility isn't always available to every member state. And of course, once a site is found, there are actual experiments that need to happen in order to confirm and validate. But these are not considered a URF. They are considered just the first stage of licensing. and supporting the regulatory approvals at that site. So now you sort of have an appreciation of what goes into sort of developing the conceptual understanding. This topic of GDFs, it's enormous. It's a mammoth task to explain the global status to a new audience. And so I wanted to introduce the concept and the validation structure first, mainly to underline that this is fundamentally a scientific undertaking. And that's really important to keep in mind as we go forward. So now you have this sort of rough idea of what GDFs are and what they're trying to achieve. Let's have a look at the process by which they start to come about and the phasing of these programs. So it should be clear that things vary from country to country as national regulations and laws differ considerably. So that's another reason why I started with the scientific basis, because that remains consistent. So on this slide, you can see that the GDF development phases, which are taken from a previous IAEA document and are included in the upcoming publication I mentioned I was an author on. This diagram charts the high-level decisions alongside each phase of a potential GDF program and maps the major elements across them. So the initiation phase can start very early in a member state's approach. It's where they acknowledge there needs to be an approach to waste management and disposal. And this is when a lot of the generic scientific studies and disposal concepts are carried out. And stakeholder engagement begins here too. The URF work we've just talked about may also start, often initially within other member states' URF programs, perhaps before advancing to developing a specific URF for that nation's requirements. And as knowledge builds and a program moves into the siting phase, this is a conscious decision by the waste management organization. They'll feel that they have sufficient underpinning to begin finding a suitable host site. So that siting approach varies significantly across the world. They're all founded on scientific principles and investigation to define the conditions, but some are more community-led than others. And again, take the UK, for example. Any local community can volunteer to take part in the siting process and can withdraw right up until just before the formal selection if they feel that it's not right for them. Compare that to Switzerland, where they've selected suitable geological areas first, then brought local communities on a journey of understanding before asking who's willing to host the GDF. In my opinion, the Swiss approach is far better for reaching an outcome and for implementation and for bringing your stakeholders along in a transparent and open way. But not every, like I say, not every approach will be suitable in every nation. It depends on the structure of policy and regulation and laws and general social sciences and how your citizens may engage with programs like this. So once a site is selected, a major program of investigations begins, verifying, and when I say investigations, I mean intrusive investigations. So you would have done all of this desk study and all of this R&D, but now you have a site and now you start validating all of that science that you've been creating. So you're verifying those conditions, you're validating the safety case assumptions, and you're supporting the facility's design and construction decisions. And that's essential for the next phase. That's the authorization for construction. This marks the transition from siting into the disposal phase. Both of these phases can last for decades, and in some cases, the disposal phase can stretch into the centuries. So during the disposal phase, construction begins and the disposal areas are commissioned. And then this is the final stage before gaining authorization for operation, when waste can finally begin being emplaced and the GDF starts its operational function. And this will be particularly tricky as GDFs will be continuously constructed and operated simultaneously for many decades. So disposal areas will be built whilst the waste emplacement happens in nearby newly completed vaults. So eventually, the GDF will then reach a point where all waste has been emplaced, disposal vaults have been backfilled and sealed, and the entire facility needs to be closed. And this requires significant work, ongoing monitoring and evaluation of the geological disposal facility's performance against the safety case to gain authorization for closure. And then the post-closure phase begins. This might include passive monitoring of the GDF, but nothing more. So remember, the entire concept here is based on being able to leave the system to passively become less radioactive over time, isolated and contained from any receptors. So now you have an appreciation for the science behind GDFs and the overall life cycle. We can sort of focus in a little bit on some of the concepts in more detail. I won't cover every member state's approach here. I mean, that would be impossible, but I'll give you a selection, pardon me, of the most different concepts. And you'll see, while the science is consistent everywhere, local regulation, geology, and stakeholder environment can still significantly impact the possible concept and outcome. So, as we sort of touched on earlier, a GDF is comprised of a natural barrier system and an engineered barrier system at depth. The facility will have underground areas allocated for disposal of specific waste types, sometimes segregated by their thermal properties. So, for instance, low heat generating waste can be spaced closer together to maximize the footprint, but higher heat generating waste needs to be spaced further apart. And this will be as geological conditions dictate. So that can increase the overall footprint. There's often a required separation between these two waste volumes as well. So if a member state also wants to emplace intermediate level waste in the same facility, that typically requires a separate area, perhaps at a shallower depth. So geology is really the main driver of how these underground layouts evolve. And but there's plenty happening above ground too. I mean, this is not just all about going underground. Surface operations handle receiving waste in specialist transport containers, managing these packages through to the through short-term storage, so they can then progress to the desired throughput in order to manage the logistics of the facility. That's also really important. The safe packaging of those waste containers to their emplacement destination at depth. This means the GDF site needs a significant transport connectivity. And for some member states, that's a combination of road, rail, and even sea connections. The surface site also will serve and does serve as the base for construction and operations. So it needs to support emergency response for any potential hazards during construction and operation. And it has a function to supply, as a supply hub, essentially, to supply the vast amount of underground work that's going on. Keep it on track, keep it supplied, keep it safe. So, offices, accommodation for workers, area for leisure and recreation, because some of these facilities could be in remote locations, all while being as minimally impactful on the local landscape as possible. So for many member states, the optimal configuration is to locate the disposal areas directly beneath the surface site. And that's, where local geology and community factors allow. It's generally the targeted outcome. However, some countries take different approaches. And again, I'll use the UK as an example. It's considering options where the surface site and the underground facilities might be separated, connected by a drift or decline access from a coastal location. And that's the bottom picture you can see there. And this was mostly driven by stakeholder, local community stakeholder perception. They really didn't feel comfortable with a disposal facility underneath where people may sort of be able to access. They liked the idea of it being away from anywhere near where anybody could be living. It's a community factor consideration, and in some cases, it's also looking at where the most volume is available. But we'll come on to talk about that just now with the role of geology. So, as I've mentioned, geology plays a crucial role in the layout of a geological disposal facility. So again, as underground engineers, you'll know our most favored approach is to work with the ground to achieve our aims. It's our partner in everything that we do. The optimal underground structure design complements the ground's natural ability to support itself. So we want to get to an efficient design with the most sustainable use of materials. So the orientation of the in situ stress field is vital in this regard. This is equally true for GDFs. The alignment of disposal areas has to make the most optimal use of the geological strata targeted for disposal. The volume isn't just about having enough space to contain all of the inventory. It's chosen for its ability, as I previously mentioned, to act as a sealing material, avoiding the creation of discontinuities that could act as potential pathways for escaped radionuclides should a scenario be, occur where the engineered barrier system fails. So the thermal, hydrological, mechanical, chemical processes, we call them THMC processes, acting on the disposal rock are absolutely vital. Many member states have targeted argillaceous rocks as their host volume. Why? Well, because of the sealing properties, their tight fracture networks and their elastoplastic behaviors that allow deformation to take place without significant damage to the host rock. Other member states, they have very different geological conditions. Hard rock, in many cases, that's so competent that any deformation is minimal, with fractures so tight and discrete that no inflows or outflows would be possible. And we previously mentioned the concept of isolation. And depth is a really important factor, really important part of that. The host volume should be deep enough to ensure that if the radionuclide does find its way into the host rock, and if that rock has fractured enough to create a pathway, the journey to a potential receptor needs to be sufficiently long. And the goal is simple in these terms. By the time that anything could possibly reach a point it can impact receptors, it would have decayed to harmless background radiation levels. So all of these geological and engineering considerations feed into something that I've been mentioning throughout the presentation, something critical called the safety case. And this is really actually fundamental to the entire story. But I've left it until this point to discuss it with you because it did require a bit of background. But hopefully it'll knit it all together. So, like I said, it's everything has been leading up to this point, really. And, everything we do impacts or forms part of a safety case for a geological disposal facility. Now, safety case isn't an unusual phrase in engineering, but it takes on a very specific meaning in the nuclear world. A safety case is the complete, structured, and evidence-based demonstration that a facility will be safe throughout its entire life cycle. So what does that actually mean in practice? Well, It brings together everything, the safety arguments that explain why the system is safe, all of your evidence and analysis from the models, experiments, data, and research. It includes the engineering design and operational controls, your risk assessments and hazard analysis. It covers management systems and governance, monitoring and assurance plans, and all of your contingency and mitigation strategies. Everything needs to work together to tell one coherent story. The purpose is clear but ambitious. We need to show regulators, government, stakeholders, and the public that the facility will protect people and the environment, not just for now, but far into the future. So we need to demonstrate that risks are properly understood and controlled, and that there's a clear, justified basis for every decision we make, and crucially, that we have the confidence in the long-term safety performance. And when I say long-term, remember we're talking thousands to hundreds of thousands of years for geological disposal facilities. For a GDF, the safety case is built using what we call the case argument evidence approach. I've just sort of kind of talked through it. That's stating your case, what you claim will happen. Then you need to support it with solid evidence that is indeed what will occur. And this is precisely why there have been decades of research undertaken in the underground research facilities. Every experiment, every model, every piece of data feeds into this evidence mix. So put simply, a safety case is the evidence backstory of safety. And it's how we prove that what we're proposing will work, not just in theory, but in reality for millennia to come. So hopefully that gives you a bit more of a broader view. When I say the word safety case, it is a really involved process. It is the very thing that defines, it's the very science that you're being asked to deliver as an underground engineer. That brings us nicely to transitioning from science to engineering, because we talk about this as being a huge science project, but actually engineers have to deliver this. So look, I hope it's clear now why undertaking a GDF is fundamentally about delivering that science of safe nuclear waste disposal. Like I said, for decades, this has been a scientific endeavor. It's building concepts, validating assumptions, undertaking investigations, and refining concepts and outcomes. But there comes a point where delivery of a GDF must begin in earnest. And when I say that, I'm talking about the end, the building of it. And look, it's my view that engineers are crucial across the entire journey of a geological disposal facility. It's both right and pragmatic that they're engaged as early as possible to help guide development towards delivery. There does come a time, however, when the volume of engineers on a program necessarily grows larger, and the program shifts from being primarily about scientific underpinning and validation to being about engineering execution and delivery. Now, there's no singular moment when this happens. I sort of see it as a phase transition, which begins during the siting phase and grows sort of from there. But others might say it's when a program goes underground for the first time, counting from when planning and investigation for that underground work begins. Overall, though, I think the transition from science to engineering is gradual, matching the life cycle of the program. There will always be scientists involved, and there will always be engineers, or there should always be engineers, but the balance will shift over time. At various points, one group may be more prevalent than the other, but both are crucial for making the right decisions. And here's something that's pretty interesting about the GDF community. It tends to exist somewhat in its own silo. It's a close-knit community, and that it does share and it collaborates well amongst fellow programs across academia and with a few select non-governmental organizations. But when it comes to industry, there's often more of an arm's length approach. So, why is that? Well, there are several reasons, I think. But, first, there haven't really been any GDFs built yet. I mean, there's WIP in the United States. Finland and Sweden are the exceptions in this regard. They're only just starting construction, so awareness in the underground engineering sector is relatively limited. And equally, the GDF community's awareness of the broader engineering sector is limited too. Second, programs have to bridge a significant capability gap, moving from scientific experimentation to major program management. That's something that's more aligned with an engineer's skill set than a research scientist's. Yet the importance of working with the industrial sector sometimes gets less emphasis. It probably should. The result then is, an understanding gap between the GDF scientific community and the engineering sector at large. There's a less than perfect appreciation of what each side needs to achieve the collective goal. And that's precisely what we're trying to address through initiatives like the ITA Special Interest Group, sort of bringing these communities together for successful delivery. They both are important for reaching the outcome, but they both need each other's expertise and understanding to get there, and one can't do it without the other. So that brings us quite nicely on to the IAEA publication that I mentioned at the start. I've just talked about the special interest group in the International Tunneling and Underground Space Association. So let me give you some insight into how that initiative actually took shape. It's directly linked to the work I was supporting the IAEA with. So it started back in spring 2021. During the pandemic, we had a virtual mission to China. The Chinese program had requested support as they were in the early stages of constructing their URF at Beishan up in the Gobi Desert in northwestern China. And so from this mission, a clear requirement emerged that we needed a publication to support member states to transitioning to going underground for a potential GDF site. The document began to take shape in 2022, and then in 2023, once we could travel again post-pandemic, we had our first in-person mission to Beishan. You can see me down there smiling in the tunnel. It was during this trip that something clicked for me and my fellow my fellow travelers and the IAEA secretary, Jerry Nieder-Westerman, who's there with me in the photo. And I was discussing with my colleagues how valuable it would be to access experts from the ITA community. The questions and the issues that were coming from this mission and we were talking about that were coming into focus were very much in the realm of the global tunneling and underground space community. And at the time, I had the support of Arnold Dix, who's the ITA president, during that period, and together we arranged for ITA experts to take part in a technical meeting, which was hosted by IAEA in Sweden. And again, this highlighted key aspects of underground construction that are crucial when planning for geological disposal. So this was so successful that the following year, ITA experts went to China to support the IAEA and the Beishan mission further. So all of this engagement demonstrated something quite important, that there's real value in these communities working together as early as possible to support global GDF programs. And that's when we began planning for a specific group within the ITA, working in partnership with the IAEA that could serve as a forum for geological disposal facility delivery. We envisioned something that was complementary to the underground research facility network I mentioned earlier, not just focused on the science, but on the engineering challenges in realizing that science science of GDF delivery. A place where key global experts would be freely and openly accessible to all of the GDF programs. So the IAEA's upcoming publication actually forms the foundation for this special interest group within the ITA. It neatly sets the stage for explaining what a GDF is and what needs to be considered before going underground at a potential site. And from there, the engineering community can step in to support the transition from concept to reality. And then taking deeper dives, no pun intended, there, into topics of value as defined by the clients, the global waste management programs. So what does this publication cover? Well, the purpose of the publication, as I've sort of alluded to there, isn't to provide deep technical analysis. Instead, it's about bringing the two communities together, scientists and engineers, around that shared understanding of geological disposal facility delivery. Now, if you're an underground engineer, you might find the later sections are quite high level. And if you're a GDF scientist, the introduction might feel like familiar territory, but that was entirely intentional. Each part was written or is written for the other audience. Our goal is to create a common baseline to foster mutual appreciation between disciplines and establish a platform from which a more detailed and specialized set of work can follow, which is the mechanism for that is the ITA special interest group. So the document covers the essential framework, the goals, the requirements,
Hi, Daniel, you have muted yourself. You're still on mute.
Can you hear me now?
Yes.
Okay, I must have lent on something. So where did I get to? Where did you stop listening? I guess
It
I'll
was
take it for
it
I'll
was just
take
a
it
second. It was a
just
second
a
ago,
second.
Dan. Yeah,
Okay,
yeah.
no problems. I'll carry on.
No
Okay.
worries.
So the document essentially covers the framework, the goals, the requirements and constraints for GDF development. It explains the concept, the safety concept for different geological settings, the program and requirements management, and crucially, what support is needed to enable that critical decision to go underground. So it also looks at the practical side, so optimizing logistics, selecting excavation and construction methods, enabling and managing construction, and planning for that full GDF delivery over its entire life cycle. So it's very clear about signposting important considerations that are often overlooked in these programs at the beginning. Things like establishing appropriate contract management strategies, implementing digital information management approaches from the very beginning, and developing the sort of comprehensive stakeholder engagement plans and supporting ongoing underground characterization that serves both the scientific and the engineering programs. So all of this kind of brings me back to a point that I touched on briefly earlier. GDF programs need to be delivered differently from most other major underground programs. So think about typical tunnel projects. They're all about speed, achieving the best advance rates possible to ensure construction is quick and on schedule. GDFs, however, are a completely different beast. Excavation might need to proceed much slower than you'd expect, and sometimes it's very much and will be very much stop-start. Why? Because we need time for scientific validation and data collection. The safety case requirements might dictate that the ground deformation stays within very specific limits, which could mean using slower and less efficient excavation methods that give us potentially better control. But here's really the significant difference. Contracts for GDF delivery might span many decades. We're talking 50, 60, even 100-year programs in some cases. So this means that contractors need to exhibit fundamentally different behaviors on these projects. Traditional contracting approaches that reward that speed and efficiency might actually work against what we're trying to achieve with these projects. So they require different contracting strategies to ensure we get the right behaviors and outcomes. Integrated project delivery teams are one tool for success, bringing the client and the contractor together in one team, with aligned objectives. But that's by no means the only approach that we can use. Alliance contracts, progressive design build arrangements, and other collaborative models. They all have their place in delivering these unique facilities successfully. So that comes on to, I've lost control a bit here. Let me move this on over here. That comes on to, well, what's the role of underground engineering community in this regard? Well, look, we're coming to the end of our time here together, and while this is an enormous subject area with so much more I could share, including how Finland is taking the first steps with their Oncolo facility, Sweden following closely behind with their Forsmark site, France just having its license for its site reviewed and accepted, and Canada drawing ever closer to beginning construction at their selected sites. I want to finish by focusing on something, again, crucial, the role of our underground community in supporting GDFs. What can you all do? So let me be direct. Apart from the obvious point that there simply isn't anyone else who can deliver these programs, our global tunneling community is the only industrial sector with the skills, expertise, and increasingly the experience to undertake these projects successfully. Underground engineers will play an essential role across every aspect of GDF delivery, in my view. You know how to create and deliver major programs safely and successfully. You understand how to translate science into something tangible and achievable. And you're skilled at working across disciplines. Tunnels are where all of the interfaces on major programs can converge. That makes you naturally capable managers of technical risk. Furthermore, we work with the ground as our partner, as I said before. So, through years of planning and designing and building underground structures, you've learned that the ground can never be taken for granted. This makes you expert in managing uncertainty and delivering safe, assured outcomes for the long term. Your logistics specialists who understand the vast amount of planning and coordination required to deliver some of the most complex structures on the planet. So this is precisely why we've established the special interest group within the ITA. This group brings together those client organizations, as I said, the waste management organizations, to identify where they need our community's support most. It's a direct channel for collaboration between those who need GDFs and those who can deliver them. Now, I imagine you're wondering, how do I get involved? How can I take advantage of this opportunity? Well, India has its own journey ahead. Our Atomic Research Centre within the Department of Atomic Energy is already working on radioactive waste management research. The Atomic Energy Regulatory board has outlined that India will eventually need to place high-level waste in geological disposal facilities. While this program is in the sort of stages of concept development, it represents a significant future opportunity. Within the ITA, you can get involved through our working groups. The special interest group on geological disposal facilities will direct specific work that waste management organizations have identified as necessary. So this topic will become increasingly visible within the ITA over the coming years. And I'm confident many of you will have opportunities to contribute your expertise. So let me leave you with this thought, one thought. There's going to be some more thoughts shortly. We're looking at centuries of work ahead. Current estimates suggest over 30 countries will need a geological disposal facility, with construction programs lasting 50 to 100 years each, if not more, followed by operational periods of a similar length. So these facilities will be among the largest and most complex underground structures ever built. They represent not just an engineering challenge, but a permanent feature of our sector's future, and one where your skills and expertise will be absolutely essential. So let me leave you with three final sort of key thoughts to take away from today's sort of talk. First, geological disposal facilities, they represent one of the most significant engineering challenges of our time. We're not just building infrastructure, we're creating structures that must function safely over long periods of time, longer than recorded human history, in fact. Every nuclear nation will need this capability, and the scale is unprecedented. Over 30 countries, hundreds of billions of investment, and programs spanning centuries. Second, this challenge sits precisely at the intersection of science and engineering. For decades, scientists have built the foundation through painstaking research in underground laboratories around the world. Now, as programs like Finland's and Sweden's move into construction, we're witnessing that crucial transition from theory to reality. And this is where your expertise becomes absolutely essential. And third, and perhaps most importantly, this is your opportunity to contribute to something truly meaningful. Through the ITA Special Interest Group on geological disposal facilities, we're creating this direct pathway for the tunneling community to engage and support these programs globally, whether through working groups, technical exchanges, or direct involvement with your national programs. There are so many ways to contribute your expertise. So the ITA publication we've discussed today, transitioning to underground construction of geological disposal facilities, will be available shortly. And I do encourage you all to read it. It's designed to bridge the gap between our communities and create that common understanding. As underground engineers, you understand better than most that the greatest structures are those built to last. With GDS, we're not just engineering for today. Or tomorrow, we're engineering for geological time. It's a responsibility, yes, but it's also an incredible privilege. So thank you for your attention today. I hope I've given you some insight into this fascinating field and inspired some of you to become part of this global endeavor. And together, we can deliver these facilities safely and successfully. Thank you.
So yeah, Daniel, it was a very informative webinar actually, and we need to actually create awareness regarding this as well. And yeah, this would be a good start for our audience as well. Thank you, and I'll pass the mic to Mr. Saurav Yele. He's one of our colleagues at TAIym. He will take on the Q&A session.
Okay.
Thank you, Daniel, for delivering such an insightful webinar on geological disposal of nuclear waste, its global progress, and IT's role toward it. Your presentation addressed critical environmental concern, the science and engineering involved in GDFs, its approaches, MBS, EPS, also highlighting URFs. And you also emphasized the essential role deep tunnels plays in overcoming these challenges. So let's move to the Q&A session. One is by Nimish. Is sealing material referred as laminated material like vermiculite? And what is purpose of rock wool in assembly shown in one of the assembly drawings?
So say that for me again. What is the purpose of?
The first one is sealing material referred as laminated mineral like vermiculite? This is the first one.
So is the sealing material doing what? Sorry.
A sealing material to seal the nuclear waste, is it a laminated material like geological laminated material like vermiculite? Is mentioning a geological feature.
Okay, so the sealing material. So there's two different types of barriers here that we're talking about. We have the engineered barrier system, and then we have the natural barrier system. So the natural, and I think maybe this question refers to the natural barrier system, which is the geological setting. And the question is asking, is it a laminated? Would you put it in a laminated geological setting? Well, that depends. So there are, for example, within the UK's program, one of the targeted disposal areas is a formation called Mercia Mudstone Group, which does have it has bedding, and it does have fractures, etc., etc. But it's about investigating the behavior of the targeted disposal depth to understand how it would react to being excavated, to being subject to having a potentially hot material placed inside because heat radiates from waste. So it's not incorrect or it's not problematic to have a laminated material, but you need to be able to prove that it meets the conditions in order to ensure safe containment. So it could be that you have a disposal geology at such a depth that the deep conditions mean that this laminated material is not going to create pathways. But on the converse side, if it has, if you're linking up through laminations or mineral alignments or discontinuities to areas that are far away from your disposal area, this is generally considered to be avoided. And what was the second part of the question?
Yeah, the second one is what is purpose of rock wool in the assembly drawing?
The purpose of rock
wool.
Right. Okay.
Yeah.
Again, this is talking about the natural barrier system, right?
Right. Yeah.
So again, your GDF works on the basis of contain and isolate. So what you want to do, your first line of defense is to construct an engineered barrier system that is not going to fail. So your waste package is of the highest possible design standards. Your bentonite backfill around the waste package is there to prevent, if the waste package does fail, any migration of the radionuclide before it gets to the natural barrier system. So you take the material design to arrest any criticality, reduce any voids in that system. Now, if it does get to the natural barrier system, you want to make sure that the radionuclide isn't going to have a pathway out of into any receptor. So, for example, that's why we talk about putting these things so deep that even if you would conceivably end up with a pathway forming due to changes in geological conditions over time, because it's very hard to predict these changes over a very long period of time. It's all about reducing uncertainty. Even if the very worst case happened and the radionuclide did find its way out of the natural barrier system, the sealing disposal area geology, it would then take so long to traverse that depth back to a point where it could potentially hit the water system and find its way to a biological receptor, that by the time that has happened, the radionuclide is decayed to alpha radiation, which is not harmful. So that is the role of the natural barrier system. It's the final line of defense. It's more about isolation than it is containment. Containment is about the natural barrier system, and containment is about the engineered barrier system, and isolation is the natural barrier system.
Yeah, the next one is from Harsha. Can you address any challenges that were faced during design or being faced in construction of Onkalo nuclear disposal facility?
No, I can't. I don't work for Onkalo. I don't work for Posiva. So you'd have to ask them that. They know their facility. So I'm sorry, I can't answer that question because I don't know.
Okay. Also, continuing with that, is there any post disposal measures developed considering possible thermal activity and its effect on stability of cavern when leaked?
Absolutely. Thermal activity is a really important part of this. I talked about the THMC processes. Now, that's important for a number of reasons. It's important to understand how heat connectivity can influence potential hazards for construction and operation, but also how when you place your waste within the ground, the waste also has a temperature. And what you don't want to do is increase the ambient temperature of the ground that then changes the THMC processes that would potentially lead to some sort of issue with containment and isolation. So these thermal processes are very important, and it's why you end up with layouts that seem quite big. So in the UK concept, the underground layout can be in some illustrative geologies can be 15 to 20 kilometers squared. And that's because the thermal properties of the rock versus the thermal properties of the waste require a degree of spacing. That means the footprint has to be quite large, even though the volume of waste is not so big. So yeah, it is an important factor.
The next one by Shubham. Like, what monitoring and retrievability strategies are being developed to ensure repository performance during operation and mainly post closure, and how frequency it should be?
That's a very, very good question. And so part of that question, I'll deal with the retrievability aspect first, because not every country has a retrievability strategy, but some do. So it's driven by member nation frameworks, requirements, regulations. But so there are some that will not bother with the retrievability question, but that doesn't take away from the monitoring. So of course, when you're developing your concept for disposal, you have a retrievability requirement, it's important to talk to engineers. That's why the engineer is an important part of this discussion very early on in the development of GDF concepts, because science may dictate that you want to dispose or place waste in a certain way, but actually it's not feasible to retrieve with current technology or engineering approaches. So this is why the engineer is important to help guide and develop those approaches and say, no, we need more research and development in this area. This is not possible yet, or this is possible, or you would want to do it in this way rather than the way that you suggest. In terms of monitoring and maintenance, well, this is really important because there are lots of things that you will want to monitor and understand from the very beginning of this program. As soon as you've selected a site, you really want to understand the baseline of that site, because that's fundamental to your safety case to prove that you've not adversely affected the baseline measurement of that site. Trust me, my battery is running low. Here we go. I'm plugged into a charger, but I think this is draining me quite a bit. It should be okay. So you want to make sure that you're measuring against that baseline. So you will have a monitoring and monitoring strategy over time to make sure that you are going through stages that validate your safety case, you're underpinning the science, and you're proving to the regulator and to your stakeholders that what you're doing is safe. When it comes down to construction and operation, again, these are important stages. You want to make sure that when you're emplacing your waste, you're meeting the safety case. What your safety case is saying that you should be doing is you're meeting that, and you do that through the monitoring approach. Post closure is a little bit different. And we were debating that here today. What things would you want to do at that stage? Well, some countries like Switzerland have a regulatory statute that says post-closure phase begins after 50 years of monitoring. Once you've closed the facility, then we say it's post-closure. because then we can say that after 50 years of closing it all up, nothing's happened, and we can walk away and leave it. And that's the whole point of a GDF, is that it's a passive system. So, you shouldn't need to do anything because your whole safety case is defined that you've done everything right and you've underpinned everything right. But of course, we're engineers and scientists. We constantly want to know whether we have done something right? So there will be, I'm sure, some approach to long-term monitoring, and the use of muon tomography, for example, which is a passive monitoring technique using natural radiation coming from cosmic ray radiation, is a very useful indicator, because this can tell you how your ground conditions are changing, how thermal, chemical, geochemical, hydrogeological conditions change over time. It's not quick. It takes a long time to get the results with the current technology state, because we're talking deep level here. We're talking 4, 5, 600,000 meters deep in some cases. But it could be a good way of monitoring in a post-closure phase. These post-closure phases are centuries away, so there'll still be more thought needed as what is required. But yeah, that's a good question.
Thank you, Daniel, for the answer and providing detailed insights.
My pleasure.
For those who couldn't attend or wish to revisit the discussion, our previous webinars are available on YouTube, and this session will be uploaded shortly after the necessary permissions are secured. We also encourage professionals to join TAIym, a dynamic platform designed to connect experts across diverse underground construction projects and share the technical knowledge. Membership offers exclusive benefits such as site visits, webinar, technical presentation, and more. So visit our website to explore upcoming activities and initiatives. Don't miss the opportunity to be part of this growing community. If you are not yet member and would like to join, please reach out to us on LinkedIn, Gmail, or website. Once again, thank you, Daniel, for sharing your expertise, and thank you all for attending. Wishing you a productive week ahead. Stay safe and happy.
Thank you.
Thank you, Daniel. Bye.
Good night.